In mathematics, we often study how a quantity responds to perturbation. But there is a deeper, less frequently asked question. What survives all perturbations? Today we explore this distinction through two canonical tools in functional analysis, the Legendre-Fenchel transform and contractive fixed-point operators. One reorganizes the description of a single function. The other identifies invariants across entire families. The Legendre-Fenchel transform establishes an involutive duality between a function f on a vector space V and its conjugate f star on the dual space V sharp. It is defined as follows. For a linear functional k, f star of k equals the supremum over x in V of the inner product of k and x minus f of x. In symbols, f star of k equals supremum over x of angle bracket k comma x angle bracket minus f of x. This construction is algebraic and pointwise. For each linear functional, it computes a supporting deviation. Geometrically, it replaces heights of the epigraph with slopes of supporting hyperplanes. The transform assumes a single, well-defined convex and lower semi-continuous function, and encodes its structure through linear probing. This makes it fundamental in variational calculus and convex optimization. Yet this duality operates intrinsically on one fixed element. It excels at describing how that element responds to infinitesimal or linear variations. It does not address stability across families of functions, nor what structure persists when functions are perturbed, rescaled, or reparameterized. For such questions, we require a different functional analytic tool. Consider a bounded invariant subset U of a Banach space, such as L2 of omega. Let T be a strictly contractive operator on U. By the Banach fixed point theorem, there exists a unique fixed point, U star. Moreover, iteration converges. U star equals the limit as k goes to infinity of t to the power k applied to U. This holds for any initial U in U. The limit is independent of initialization. The operator collapses an entire family to a single stable representative, characterized not by dual slopes, but by maximal regularity and stability. This is not duality. It is not re-expression. It is closure. Distinct realizations become indistinguishable under iteration. The fixed point embodies persistence. What survives perturbation? In infinite dimensional spaces, such operators arise naturally in nonlinear partial differential equations, producing unique, stable solutions from bounded classes of initial data. We now see the essential distinction. Legendre-Fenchel duality reorganizes a single function via supremal convolution with linear functionals. Contractive fixed-point operators identify equivalence classes through convergence to a unique invariant. One concerns response and representation, the other concerns persistence and structural stability. They are complementary tools, not competitors. In partial differential equations, duality dominates convex variational problems and optimal control. Contractive methods establish well-posedness, regularization, and stability for nonlinear evolution equations. Both are indispensable in modern analysis. Legendre-Fenchel duality exchanges values for slopes within a single function. Contractive closure exchanges diverse realizations for shared invariants. Both constructions are canonical. They simply answer different analytical questions. Thank you for watching.